Well, hello everyone. Now in this lesson, we're going to kind of venture more into vector operations. So we talked about attributes of vectors before, but now we're actually going to do a little bit more operations with them. So just to start off, 1 through 4 here is going to be kind of a recap of the first lesson. So we're going to do all 4 of these questions just to kind of make sure that we're good on these skills. So just to warm up, you're going to sketch the vector and then determine the exact component form. Now, when I say component form, you're going to be writing your vectors in the form of x comma y with these quote-unquote parentheses. So they're not going to be parentheses. They look like inequality signs, but I call them parentheses just because they're not necessarily parentheses, but we want to indicate that we're working with a vector. So looking at this very first one, we have a magnitude of 4 centimeters and a direction of 30 degrees north of west. So for 30 degrees north of west, we're going to start with our direction. So I want to go in the direction of west, but then I'm going to go northbound. So this entire angle that was right here that we kind of went through, that's the angle that we're referring to. So right here, this would be our vector, which is going to have a magnitude of 4 centimeters. And then from that direction, that's going to contain 30 degrees. So our theta value here will be 30 degrees. Now with component form, what's also really important is that your angles must be in standard position. So your angles may be given using the cardinal directions like the north of west or west of south or east of south or whatever. But whenever you're writing your angle in terms of component form, we have to make sure that we're writing it in terms of standard position. So with standard position, you're going to start in the positive x-axis, and then we're going to measure our angle going counterclockwise. So we want to be able to figure out what this theta value is. So what we're going to do is I look and see that straight across is going to be 180 degrees. And then we have this portion of the angle, which is going to be 30 degrees. So I want to figure out what's left right here. So to find that angle, what I can do is I can do 180 degrees minus the 30 degrees that we have, which tells me that this angle right here in standard position is going to be 150 degrees. So for component form, so I'm going to write it out using the parentheses in x comma y, and I'm going to do the magnitude of that vector times cosine of that angle, and then I'm going to do the magnitude once again times sine of that angle. That way we can have our component form. So the magnitude in this question they gave us is 4. So we're going to do 4 times cosine of this angle in standard position, which is going to be 150, and then 4 times sine of 150. So these values we can find from the unit circle, so we're just going to go directly to the unit circle. So we're going to do 4 times cosine of 150 degrees, which is the same as 5 pi over 6, which is going to be negative root 3 over 2. And then we're going to do 4 times sine of 150, which is going to be 1/2, which when we simplify, our component form here will be negative 2 root 3, comma 2. So this would be your component form. Now moving over to number 2, same idea. Now we have a magnitude of 12 meters and a direction of 52 degrees east of south. So to draw this vector, I want to go towards south, and then I want to go east of this southbound direction. So I'm going to go directly to the right. Whoops, let's do a little bit more since it's 52. It's a little bit more than halfway. So the magnitude here, which would be 12 meters, yes. And then they also tell us that the angle right here would be 52 degrees. So once again, that's not in standard position. Standard position is going to start at the positive x-axis and measure that angle going counterclockwise. So we're going to go all the way around. So what I notice is that this angle goes through the first quadrant, the second quadrant, and the third quadrant all together, and then an additional 52 degrees. So this theta value right here is going to go through 3 quadrants, which means we're going to do 3 times 90, and then plus an additional 52 degrees. So that 3 times 90 is going to be 270 degrees, plus 52 degrees, which means we're going to be working with an angle of 322 degrees. So when I write my component form, so I'm going to do my magnitude, which is going to be 12 times cosine of 322, and then comma 12 times sine of 322. Now 322 degrees is not going to be on the unit circle, so if I just want the exact form, then this would be what we want. So you could leave it just like this if it was a non-calculator question. However, if it is a calculator question, then you can actually go to your calculator and we can actually plug this in and find the approximate, which would be the decimal. So down below, this would be the approximate, which is what we're about to do. Now, when you plug this in on your calculator, a very important note is you must make sure that we are in degree mode. So you are going to be responsible for making sure that you're in the right mode on assessments. Now, when you reset your calculator, just know that your calculators are going to default to radian mode. So if you reset, you got to make sure you put it back in degree mode. So I'm going to type in 12 cosine of 322 on my calculator, and then I'm going to round this value to 3 decimal places, which is going to give me 9.456. And then I'm going to do 12 sine of 322, which is going to give me negative 7.388. So this would be your component form after rounding. And then, of course, you're going to check your directions, and you're going to determine if we want the exact form, if we want the approximate form. It'll pretty much tell you in the directions what we want. But either one of these would be accepted, contingent on the directions, of course. Now below for 3 and 4, now we want to sketch the vector, then determine the magnitude and the direction. So I give you a vector 4, 3. So 4, 3 is going to put us in quadrant 1. So it'll be something like this. And then what I'm going to do is I'm going to triangulate. So I'm going to turn this into a triangle so that I can see a clear x and a clear y component. So based on my vector here, I know that my x component would be 4. I know my y component would be 3. So I'm going to have 4 and 3 labeled on my diagram. And then what we're looking for is going to be the magnitude of this vector. And then we're going to look for the angle, which is going to be the direction. So your magnitude is going to be doing Pythagorean theorem. So I'm just going to do the square root of my x component squared plus my y component squared, which this is going to give me the square root of 4 squared plus 3 squared, which if you remember your Pythagorean triples, this would give you the square root of 25, which would be 5. So we have a 3, 4, 5 triangle. And then if I'm looking for the direction, then we're going to do inverse tangent. So inverse tangent of the opposite over the adjacent, so your y value over your x value, which means we're going to do inverse tangent of 3 over 4. So when you plug this in, so that's not on the unit circle, so we're going to have to use a calculator for this if we want the decimal form, or the approximate form rather. So inverse tangent, and I'm going to do 3 over 4, which is going to give us a degree of 36.86989. Now, since I want to round to just 3 decimal places, that's going to round to 87 degrees. Now, this is in standard position already, so I don't need to do any adjustments. However, if I wanted to include any like cardinal directions, then this means I would have a theta value. Come on, there we go. This would be 36.87 degrees north of east, if I really wanted to account for the cardinal directions. Now, if I also wanted to account for doing the other angle in quadrant 1, so I could do like this other theta value over here. So I'll just leave it in green so we can color code. So if I wanted to find my angle in terms of east of north, then what you're going to do is you're going to take your angle that we just got in pink, and you're going to do 90 minus theta. So I'm going to do 90 minus that 36, which means if I want to do the other angle, that'd be 53.13 degrees east of north. So depending on the question, depending on what type of angle it wants, if I want standard position, that's what your inverse tangent is going to give you. Then you can manipulate your standard position into your cardinal directions if you need to. So there's 3 different ways that we could read this. Standard position, which is the 36.87 degrees. And then if I do the cardinal direction in quadrant 1, that would be 36.87 degrees north of east. Or I could even do 53.13 degrees east of north. So I would suggest you actually pause here and actually try number 4 on your own. Now with number 4, we have the vector -6, -2, which is going to put us in quadrant 3. So it looks something like this. And of course, I'm still going to triangulate, so I can do the same process. So with this, I know I'm going to have an x component of -6 and a y component of -2. And then what we want to find is going to be the magnitude of this vector. And then we also need to find the direction of this vector. Now, keep in mind with the direction of this vector, notice how it's not going to be read in standard position. Or rather, when we do inverse tangent, let me kind of change this up a smidge. When we do inverse tangent, it's actually going to give us the angle in standard position. So we're actually going to have to alter the angle in standard position in order to get those cardinal directions. So to start off, let's go ahead and do our magnitude. So the magnitude is going to be doing Pythagorean theorem. So I want square root of -6 squared plus -2 squared. So that's going to be square root of 36 plus 4, which is going to give me the square root of 40. Now I'm going to do prime factorization super quick. Whoops. So I want to simplify the square root of 40, so I'm going to find 2 factors that multiply to 40. It could be any 2 factors. So I'm going to do 2 and 20. Then 20 splits into 2 and 10. 10 splits into 2 and 5. So what we're doing here is we're looking for the prime factors. Once the number branches off and splits, we no longer need that number for when we do this last part. So what we're doing is we're going to look for numbers in pairs. So I have a pair of 2's here, but then I have a 2 and a 5 that did not pair off. So the numbers that pair off are going to go on the outside of the radical, and the numbers that did not pair off are going to stay inside the radical. So because I have a pair of 2's on the outside, I'm only going to write that number one singular time. And then we still have that 2 and the 5 that didn't pair off, so those are going to stay inside the radical. So this would simplify to be 2 root 10. So this would be your magnitude. So now we still need to do our direction. Now our vector here is going to be in quadrant 3. So because we're in quadrant 3, what that technically means is we need to add 180 degrees. Because when you do inverse tangent is only going to let you work in quadrant 1 and quadrant 4. We're not going to be able to find values in 2 or 3. So if I go to quadrant, or if I need my value in quadrant 3, we're actually going to find the value in quadrant 1, and then we're going to add 180 degrees to move it to quadrant 3. So when I find my direction, so I'm going to do theta equals inverse tangent of my y value over my x value. So I'm going to do -2 over -6. So this is going to be inverse tangent of a third. Now that's not on the unit circle, so we have to go to the calculator. So inverse tangent of 1/3 which is going to give me 18.435 degrees. So I was actually wrong about this part over here. That is my fault. My apologies. So what we just got was this angle right here. So this was the 18.435 degrees. So I know in terms of vertical angles, I know that this angle right here, the 18.435 that we just got, is going to be equal to this angle across from it. So that means in order to find the quadrant 3 value in standard position, so standard position, means I'm going to do that theta value plus 180. So in standard position, our angle is actually 198.435 degrees. Now, if I want to consider doing the cardinal directions, that's where we're going to use the 18.435. So the 18.345, that is also this angle right here. So I could also write it as 18.435 degrees south of west. And then if I want the other one, which means I would flip it and it would become west of south, which means I would be finding this angle right here, then I would do $90 minus that theta value. So I would do 90 minus 18.43494,882, which is what I have on my calculator. And then that is going to give me 71.565 degrees. So if I want the angle in standard position, I would want 198.435 degrees. Or if I want the cardinal directions, I could ask you for either one of these directions. So moving on, so now we're going to go into vector operations, which is kind of venturing into the newer topics that we're looking at. So what we're going to be doing is we're going to be given several vectors, and we're going to be doing just the basic operations. So adding, subtracting, multiplying. We're not going to divide, thankfully, but we're just going to stick to adding, subtracting, and multiplying. So whenever we do operations to these vectors, the resultant is what happens as a result. So hopefully that kind of goes with the name. So if I were to multiply a vector, or if I add a vector to something, the product is what we call the resultant vector. Now, looking at some characteristics, if we have a negative vector, what's going to happen is we're just going to go 180 degrees in the opposite direction. So, for example, if I start with a vector that goes up and to the right, but then I make it negative, what's going to happen is now it's just going to go down and to the left. So notice how the only thing that changed is the direction. The magnitude stayed the same. The length of the vector is the same. All we did was we just flipped the direction. So if we multiply a vector by what we call a scalar, which is almost like a coefficient, then that means that the length or the magnitude of that vector is also going to be altered. So if we multiply by a scalar that is more than 1, that means the vector is going to get longer. Whereas if the scalar is multiplied by something between 0 and 1, so if I do like 1/2 or 2/3 or 3/4, then that means it's going to get shorter, since we're essentially multiplying by something smaller than 1. And then, of course, if the scalar is negative, as we just mentioned, that means it's going to go in the opposite direction. But more specifically, 180 degrees in the opposite direction. So looking at this chart, hopefully this looks familiar, we're going to be given any sort of combination of vectors, and we're going to perform the indicated operations. So for the very first one, I have vector A plus vector C. So I first want to write each of these vectors in component form. So if I look at vector A over here, I know I'm going up 2 and then right 1. So I want to write this in terms of x comma y. So with vector A, I have an x component of 1 and a y component of 2. And then for vector c, we're going to go down here. Well, I went from the initial point to the terminal side. We're going to go 1, 2, 3 to the right, and then 1 up, which means my component form would be 3, 1. So when I add these two vectors together, I'm going to write them individually first, actually. So this is going to give me a 2, 1. And then vector c, we're looking at 3, 1. So when I add them together, think of it almost like combining like terms. I want to write my x components together, but then I want to write my y components together. So when we do this, then we're going to have a result. Ooh, can I not do math? Nope, I got it backwards. Sorry, y'all. My bad, my bad. It's 1, 2. I knew something didn't look right. So then this is going to change and become 1 plus 3, and then 2 plus 1. Sorry, y'all. So we're going to have 1 plus 3, which is going to be 4, and then 2 plus 1, which is going to give me 3. So then this would be component form, which is your resultant vector. So component form of the resultant vector. So we can do it algebraically, which is what I just did. Thankfully, I caught that mistake. Now over here, I also give you these graphs. So we can do it graphically as well. So what I'm going to do is I'm going to draw both of my vectors together. So I'm going to draw anywhere on my graph, say vector A, which I'll say this is vector A. And then we have vector C. So when we add it together, I want to connect them from head to tail, meaning vector C, I'm going to rewrite and connect it from vector A. So now, once I rewrite both of my vectors on the graph and they're connected head to tail, you can see that we kind of have 2 out of 3 sides of a triangle. So when I draw that final side of my triangle, this is actually going to be your resultant vector. So if you find the component form of this resultant vector, I can look at the x component and the y component of this vector. So if I start at the initial side and I want to end at the terminal side, I can count 1, 2, 3, 4 for my x values, and then I can count up 1, 2, 3, which is going to be my y component, which that is what matches this. So we're good. So once again, you could do it algebraically or you could do it graphically. No matter how you do it, you should get the same thing. So now we're going to look at number 2. So number 2, notice how we have a negative e plus d. So negative e is going to be, we're going to use vector e. So what I'm going to do is I'm going to alter this graph because I'm only going to use these 2 problems for these. So I'm going to change this to a negative e. Now what's going to happen is notice how your terminal side is going up and to the right. When we make it negative, now it's actually going to go the other way. So now my initial side would be over here, and then my terminal side will now be going this way. So I just took that vector and I just made it go the opposite direction. So when I think about negative e, well, actually, let's do positive e first. Positive e in component form would be 1, 2. But if I now have a negative e, what we're doing is we're making both of these components negative. So essentially, we're kind of quote-unquote distributing that negative. So over here, I'm going to use negative vector e, and I'm going to write this vector as -1, -2. And then vector d, we're going to look at this vector over here. So I'm going to start with the terminal side, and then we're going to end with the terminal side. Or start with the initial side, end with the terminal side. Sorry, y'all. So when I look at my x component, I'm going to count 1, 2, 3, 4, 5. So that would be my x component. And then I'm going to count up just 1, which would be my y component. So that tells me that my component form for this vector would be 5, 1. So now I want to be able to combine these. So when I do negative e or negative vector E plus vector D, I'm going to combine the x components together and then combine the y components together. So I'm going to do negative 1 plus 5, and then negative 2 plus 1. So as a result, this would give me positive 4, comma, negative 1. So this would be your resultant vector of this vector operation. So now I'm going to go over here to the graph, and I'm going to show you what it's going to look like graphically. So negative E is going to be going downwards like this. So here's negative vector E. And then I want to combine it with vector D, which is going to be 5, comma 1. So I'm going to actually move this over a bit. So then for vector D, I'm going to go 1, 2, 3, 4, 5, and then up 1. So then here's vector D. And then your resultant vector, we're going to combine and essentially close that last side of that triangle. So when I look at the components of this triangle, my vector component would be 1, 2, 3, 4 for my x value, and then I would go down 1 for my y value. So we still get the same thing no matter how we do it. Now moving on to the next part. So this is just a bunch, not really a bunch, but this is just several more examples of doing essentially the exact same thing. So 3 and 4 are doing essentially the same thing. 5, 6, 7, and 8 are doing the same thing. It's just going to be written in a different way. So I'm actually going to move down here to the equilibrium section. So what we want to do is we want to determine what vector is going to create equilibrium if applied to a resultant force. So when I mention equilibrium here, this means I want the resultant to equal 0, comma 0. So essentially, what force do I need to apply to it in order for this vector to just result in 0? So when I look at my vectors here, what I want to do is I just want to negate what I'm already doing. So if I have a vector of 6, comma negative 2, then that means in order to obtain equilibrium, I need negative 6, comma positive 2. So I just need to flip the signs. So then for number 10, my resultant vector here to create equilibrium would be 0, comma 4. So yeah, if I just give you your component forms of these vectors, then all you're going to do is just flip the signs. Now, if I decide to be a little bit more on the spicy side, then I'm actually going to give you the magnitude and a direction of a vector. So this is going to be more visual. So for number 11, I give you a magnitude of 5 and the direction of 40 degrees. So I'm going to draw a cute little picture. So I'm going to go 40 degrees in standard position. And then this would be a magnitude of 5. Now, for it to be equilibrium, I need it to essentially zero out. So I need the same magnitude, but I need it to go the opposite direction. So I'm going to have a magnitude of 5, but what I need to figure out is what is going to be this angle right here. That's what I need to determine. So this angle right here is going to be 180 plus 40 degrees if I want to find it in standard position. So that means this is going to be 220 degrees. So the way that you would answer this is you would say, I need a vector with the magnitude of 5 going in the direction of 220 degrees. So this is how you would answer that. So a vector with magnitude of 5 going at a direction of 220 degrees. Now with number 12, same idea, we need a vector to be essentially zeroed out. So I have a vector with a magnitude of 2 going in the direction of 300 degrees. So with this vector, 300 degrees is going to put us in quadrant 4. So this is going to be a vector with 2. And I know this angle right here is going to be 300 degrees. So I need an equal and opposite reaction, essentially, in order for this to zero out. So this magnitude will also be 2, but I need to figure out what is this angle right here going to be in standard form. So in order to find that angle, what I'm going to do is if I know that this angle right here in blue, if I know this is 300, then that means I want to essentially send it back 180 degrees. So in order to find that angle, what I'm going to do is I'm going to do the original angle, which is 300, minus 180 degrees. So then that tells you that our angle in the opposite direction is going to go towards 120 degrees. So for this problem, we're going to want a vector that has a magnitude of 2 going in the direction of 120 degrees. So this would be how we answer this question. And now looking down here, so these are going to be kind of your summary problems is kind of, I guess, how I would call it. So this is rude. So this is kind of putting everything together. So we're going to be given 2 different vectors with a given magnitude and direction, and then we want to find the resultant vector and then find the resultant vector's direction and magnitude. So to start off, we're given 2 vectors. So with vector v, I'm going to write vector v. I'm going to give it this whole little section over here. So I'm going to write this one in component form. So in component form, I'm going to do the magnitude, then cosine of that angle, which is 150 degrees, and then the magnitude times sine of 150 degrees. And then this is going to give me 4 times negative root 3 over 2, comma, 4 times positive 1/2, since these are evaluated using the unit circle. And then this is going to be equal to negative 2 root 3, comma, positive 2. So here is my component form of vector v. Now I need to do component form of vector u. So for vector u, I'm going to do 3 times cosine of 60 degrees, and then 3 times sine of 60 degrees. So then I'm going to evaluate using the unit circle, which if it's not in the unit circle, then you would use your calculator. So this would be 3 times cosine of 60, which is going to be 1/2, and then 3 times sine of 60, which is going to be root 3 over 2. And then, of course, when you simplify, this is going to be equal to 3/2, comma, 3 root 3 over 2. So we have both of our vectors written in component form. Now we want to find the resultant. Now the resultant is going to be when we combine both of these radicals together. So meaning, I'm going to do vector v plus vector u. And I'm going to combine the x component, so I'm going to do negative 2 root 3 plus 3/2. And then I'm going to combine the y values, so 2 plus 3 root 3 over 2. So this would be an acceptable way to write the component form in exact. I'm totally fine with doing it that way. When you plug these in on the calculator, it is going to give you a different form, which I'm going to plug these in on the calculator, which I don't know actually why I'm plugging these in. I can just do it by hand. So never mind. Let me put my calculator up. So I have a denominator of 2 right here. So I need a denominator of 2 over here so I can combine these. So that just means I need to multiply this 2 right here times 2, which means I'm going to have negative 4 root 3 plus 3, and then this would be all over 2. And then same idea over here. I need this to be a denominator of 2 in order to combine, which means I need to multiply this times 2, which means that numerator is going to become a 4. So then this would be 4 plus 3 root 3 over 2. So that would be my component form written in exact form. So negative 4 root 3 plus 3 over 2. And then 4 plus 3 root 3 over 2, which is going to be exact. And now where I have approximate, that's going to be where I want the decimals. So if I were to plug these in and I get the decimal, then that's going to give me negative 1.964, comma, and then plugging in the second one, I'd get 5.598. Now, another really big bit of information that may not be as obviously presented to you is look at the quadrant that this vector would happen in. If I have a negative and a positive, that tells me that this is going to happen in quadrant 2. So I'm going to need that information for when I do the direction. Because for the direction, because I'm in quadrant 2, that means I need to do the angle plus 180 degrees. So we're going to start with the magnitude, actually. So the magnitude is going to be the absolute value of vector v plus vector u. And I'm going to do Pythagorean theorem. Now, these are going to be really gross looking, but it's okay. So I'm going to do negative 4 root 3 plus 3, all divided by 2, squared, plus 4 plus 3 root 3 over 2 squared. So when you plug this in, ironically enough, well, I'll actually kind of stop and give you a second to plug it in. So I want you to plug it in. I want you to see what you get. Because then when I plug it in, what I get is 5. So now I know the magnitude is going to be 5, so I can write that down here for the magnitude. Now we need to find the direction. Now remember, for the direction, we're going to have to add 180 degrees to whatever you get. So for your theta value, so I'm going to do inverse tangent. I'm just going to do a big parenthesis. So I want the y component over the x component. So I want to do 4 plus 3 root 3 divided by 2 over negative 4 root 3 plus 3 divided by 2. And then I want to plug that in for inverse tangent. So when you plug this in, once again, I'll give you a second. I want you to plug it in. So pause if you need to. So once you plug it in, I get negative 66.8699, which is going to round. You need to round to 3 decimals, but when you round, it's going to round to 2. So it's going to be negative 66.87 degrees. But because we need to be in quadrant 2, I need to add 180 degrees, which means your theta value is actually going to be 113.130. So it's just going to be 113.13 degrees. I cannot write. There we go. Now, also be prepared for doing this part in cardinal directions as well. So I could ask you to do other cardinal directions. Now, because this quadrant, or because this vector falls in quadrant 2, then I could ask you to do the direction in something north of west, or I could ask you west of north, since it's in quadrant 2. So be prepared for those as well. So, ta-da!